Start plus steady change. Every line says this. Hear it out.
Here in the Symmetree Learning Grove, mathematical quantities are physically carved into the natural environment. By watching how animals move through this space, we can observe relationships before we ever assign them a mathematical name. Consider a taxi journey through the grove. This ride begins with a flat $4 start fee, and then the cost increases by $2.50 for every mile traveled. That flat $4 fee at the starting stone is the initial value, recorded as B equals 4. As the journey continues, it charges $2.50 for each mile. The rate of change, M equals 2.5, encountered with every step. Placing this repeating cost and fixed start fee into our y equals mx plus b template yields the final equation, y equals 2.5x plus 4. Verbal cues like starting and each are strict mathematical instructions. They dictate exactly which number is the fixed initial value and which acts as the growing multiplier for every mile the animal travels. Linear relationships also appear in discrete data sequences, where each step represents a specific recorded value. This sequence of lily pads maps hours worked to total earnings. 0 hours yields $18, 1 hour yields 24, 2 hours yields 30, and 3 hours yields 36. To find the initial value, we hunt for the entry where the independent variable is exactly 0. Because the animal starts its journey at $18 before any hours pass, our B value is 18. Next, we measure the change between steps. Each leap the animal takes adds exactly $6, establishing our constant rate of change at 6. Plugging that 0 state and the constant $6 increase into our standard format yields the linear equation y equals 6x plus 18. Defaulting to the very first number you see in a dataset is a trap. The true initial value only exists where the independent variable is 0, the very first pad where the animal's journey began. When we plot these relationships on a graph, we can extract the same values by observing how the animal changes its physical elevation.
Find the starting value. Find the rate. Then write the rule.
Looking at this stone structure, we locate the starting point by finding where the path crosses the vertical y-axis. Resting on this axis means the horizontal x value is 0. Since the animal is at an elevation of 12 before moving forward, our initial value b is 12. To find the rate of change, we look at where the animal climbs next. Following the line upward, we find a stone marked 3:21. Between the base and this higher stone, take a moment to calculate the vertical rise and the horizontal run of the animal's path. From an elevation of 12 up to 21, the vertical rise is 9. Across 3 units of horizontal distance, the run is 3. Dividing that rise by the run gives us a rate of 3 and a final equation of y equals 3x plus 12. Mathematical slope is a measurement of physical elevation change. The rate of change dictates exactly how steeply the animal must climb to reach the next point. Every method we've used, words, tables, and graphs, maps back to the same natural laws of the grove. We've built 3 distinct models, one from the rhythm of a journey, one from a sequence of leaps across the water, and one from the steepness of a climb. Regardless of how the data is presented, the core template relies entirely on identifying what is fixed at the start and what is moving as the journey unfolds. Mathematical notation is a record of these physical relationships. Which specific mark in this environment proves the truth of the equations you just built, and how does the animal's action make that relationship true?
Rate and start found. The function is yours. Model something real.